We're going to be talking about solving trigonometric equations. And a trigonometric equation is an equation that has sine, cosine, tangent, cotangent, cosecant, etc. So I recommend that you have your own unit circle to look at as you're doing these. You might want to just go through the problems on your own as I'm going through them. You might be able to figure some of them out without me even showing you. So I do recommend that you try that. So for my first example, we have cosine of theta is equal to radical 3 over 2. So we are going to solve this equation. And when you're asked to solve, that means that you need to find a variable. So we are going to be looking for the theta. You might notice that this is really similar to what we were doing in the last section where we were talking about inverse functions. And it actually is pretty much the same thing. If you had, you don't need to write this down, but if you had inverse cosine of radical 3 over 2, that's the exact same thing as what I'm looking for now. Just looking for the angle. I think this is a little easier personally, although some of the problems do tend to get a little bit harder. So I'm hoping that you think this is easier than the inverse functions. Okay, so for this one, the one thing that is different from inverse functions is that inverse functions have a domain. So like the answer for this one, your theta, is always between 0 and pi. That is not the case for cosine of theta equals radical 3 over 2. For that one, you do not have a set domain unless you are actually given a domain. So we are not going to use a domain here unless they tell us. In fact, they usually will tell you, but for the first one, I'm not going to tell you the domain. I'll show you how to write it if you're not given a domain. All right, so for this one, what we want to do is we want to figure out all of the places on the unit circle where cosine is equal to radical 3 over 2. Remember, cosine is my x value, so you'll hopefully notice that happens right here, and that also happens right here. So I end up getting that my theta is equal to pi over 6 and 11 pi over 6. Okay, now here's the thing that gets confusing for some people. And that thing is that if you were to go around the unit circle one more time, and you would end up here, which would be at pi over 6 plus 2 pi, that's actually 13 pi over 6 right there, that would give you another answer. Or alternatively, if you were to go in this direction, that would give you another answer. That would be at negative pi over 6. And actually, you have an infinite number of answers here. So we're not going to write down all the answers. We would be writing forever and ever and ever. That's not a good way to spend your life. So instead of doing that, we are going to use a similar notation to something that we saw in the past. We're going to take each of the two basic ones that we saw in the unit circle, which were the pi over 6 and the 11 pi over 6. So we know that if we were to take pi over 6 and either add or subtract 2 pi, we would actually get, so I'm going to say plus 2 pi, we would actually get the same value. The same thing would happen if we added 4 pi, or if we added 6 pi, or if we subtracted 4 pi, or if we subtracted 6 pi. So the way that we're going to write it is as pi over 6 plus 2 pi times k. And in that case, k is any integer. And keep in mind, integers could be positive or negative, so that takes into account the negative things when we were subtracting 2 pi. Same thing for 11 pi over 6. We're going to do plus 2 pi k, or actually we usually write it as 2k pi would be the more common way of writing it. Same thing, k is any integer. So these are our two answers for this. You can write it like this if you must write it like this if you're not given a domain. However, I am going to give you a domain for most of these. Just keep in mind that there are going to be some occasions where you're not given a domain in the beginning. But let's do one of those examples where we do have a domain. So here's my second problem. This one I did give you a domain. 0 is less than or equal to theta is less than 2 pi. That means that we are only going to have values in our answer that appear on the unit circle. You're not going to have to worry about that 2k pi or anything, which is pretty nice. So the way that you're going to solve this is the same way that you solve any other equation. You can think of that sine theta as being similar to a variable. So I'm going to move over the radical 2. I get negative radical 2 on the right side. Then I divide both sides by 2. I get sine of theta is equal to negative radical 2 over 2. Now you're just going to look on your unit circle and see if you can find the places where your sine value is negative radical 2 over 2. And that occurs at 5 pi over 4. And it also occurs at 7 pi over 4. Once again, we don't need to worry about a k pi, 2k pi, because we have been given a domain that's on the unit circle, which is really nice. Here's another one. This one's a little strange. You're welcome to try it on your own, or at least try to get started on it if you want. So we want to know what are the theta values where cosine of 2 theta is equal to 1/2. So you're going to start this problem similar to the other problems that you've done. You will find that cosine of any of the angle pi over 3 is going to give you 1/2. So actually we are going to get that our angle is equal to pi over 3. Here's the thing. Our angle is not theta. It's actually 2 theta. So we're going to get that 2 theta is equal to pi over 3. And that is going to give us that theta is equal to pi over 6. Okay, here's the other thing that's weird. Because cosine of 2 theta has a period of pi and not 2 pi, we are actually going to get an additional solution that's between 0 and pi. I'll show you what I mean if you're a little bit confused about that. So we found right here that our angle was pi over 3. That was the angle where the cosine was equal to 1/2. Cosine is going to be equal to 1/2 also at 5 pi over 3. And you might be thinking, well, 5 pi over 3 isn't in that domain that I gave you. However, if we solve the 2 pi is equal to 5 pi over 3, suddenly what's going to happen is when you divide both sides by 2, you get that theta is equal to 5 pi over 6. That is within the domain. So actually, this is also one of the answers. Be really careful when you see these types of problems. They're a little challenging. We'll do some more examples on these, though. Before we do our last example, I want to review one thing that we talked about previously, and that is the Pythagorean identity. Sine squared theta plus cosine squared theta is equal to 1. This is a really important identity, and we're going to use it extensively. You see this one a lot. In addition to having this identity, you also can take this identity and solve it for either sine squared theta or cosine squared theta. So like an equivalent identity is if you have sine squared theta is equal to 1 minus cosine squared theta. And we can also write cosine squared theta is equal to 1 minus sine squared theta. So this top identity is really important. If you don't have it memorized already, I'd recommend that you just memorize this one. You're going to see it so often that it's a good one to have in your mind. The 2 at the bottom you can just get by rearranging the terms of the top one. So I wouldn't memorize those ones too, unless you're super good at memorizing. But keep those in mind. We're going to do an example, and we will actually use one of those. So there's quite a bit of stuff going on with this problem. Right now, it just looks like a hard problem. So when you have an equation and you have sines and cosines in it, it is almost always necessary to rewrite it so you either have only sines or only cosines. Now, we don't have an identity with cosines that'll give us sines based on just having a cosine of theta. We can't really do anything to that. However, what we can do is we can take this sine squared and we can replace it with this thing that we have up there. Then we'll have an equation with only cosines. So let's go ahead and do that. And you might think that you have done all of the hard stuff in this problem. Unfortunately, there's still a few more challenging things to do. So you can see I distributed that too. Now what I'm going to do is try to see what I can do, if I can put any cosines together. By the way, I cannot. I have a cosine squared, and I have a cosine, and then I have a bunch of numbers. Actually, if I get something like this, this is a form of a quadratic equation. So I'll show you what I'm going to do for this. I'm going to first move the cosine squared over to the left side, the 2 cosine squared. It becomes positive when I move it over. I do recommend that whatever your squared term is should be positive. I'm also going to subtract the 2 on the right from both sides, which gives me 1. This equation, it might look similar to something that you've seen before, or you might just be looking at it like, what is going on here? But this is actually a similar equation to the equation 2x squared plus 3x plus 1. You'll notice that instead of x's, however, I have cosine thetas. So keep in mind that cosine squared theta is the same as cosine of theta squared. That's something people sometimes forget. So you can think of it as if the x has been replaced with the cosine, if that makes it easier. There are a few ways to solve this problem. Probably the easiest way to do it is going to be by factoring. So if you were to factor 2x squared plus 3x plus 1, you would get 2x plus 1 times x plus 1. That would be what we would get if we had x's. We don't have x's, but we can actually do the same pattern, but with cosines. So we're going to write it as 2 cosine plus 1 times cosine plus 1. Be careful, now that we factor it, we no longer have that squared term there. If you want, you can check your work by trying to use the FOIL method and multiply it back together. You will get what you started with above. So now what we can do is we can use the same process that we did when we factored and solved equations like this back in Algebra 1, Algebra 2. We are going to set each factor equal to 0. So I set 2 cosine theta plus 1 equal to 0, and I set cosine theta plus 1 equals 0. And I actually forgot to give you the domain, but I am definitely going to give you the domain here. It's a lot easier to have it. So we are going to be looking for a theta value between 0 and 2 pi. Okay, so the one on the left, 2 cosine theta plus 1 equals 0. If you solve for that cosine theta, you move the 1 over, you get negative 1, and then you divide by that 2, you get negative 1/2. That gives us theta is equal to, we have 2 answers. We have one at 2 pi over 3, and we have one at 4 pi over 3. So there are 2 answers from that one. It's going to occur everywhere that we have a cosine equal to -1/2. The next one that we have, cosine theta plus 1 equals 0, I'm going to rewrite that as cosine theta is equal to -1. That actually only occurs in one place. It occurs right here where theta is equal to pi. So that's going to be my answer for that one. So my 3 answers are going to be pi, 2 pi over 3, and 4 pi over 3.